Hello everyone. In this lesson we will study about aryl halides. Alkyl halides and aryl halides are two different types of compounds, composed of hydrogen and carbon. In these hydrocarbons, one or more hydrogen atoms is replaced by a halogen. Therefore aryl halides are also known as haloaryns. In the content we are going to cover: introduction of aryl halide, its preparation, and reactivity towards nucleophilic substitution reaction of different types of halides. Introduction. What is aryl halide? Aryl halide are derivative of aromatic hydrocarbons, in which halogen atom are directly attached to carbon atom, by the replacement of hydrogen atom. If more than one halogen is present, then the name of halogen is preceded by the prefix di, tri, tetra etc. to signify the number of halogen atom present. The position of halogen atom is indicated by the use of number or prefix that is ortho, meta, or para. See these picture. Here the fluorobenzene, chlorobenzene, bromobenzene, and iodobenzene are example or aryl halide. Aryl halides are organic compounds with the general formula Rx, where R denotes the aryl group and X denotes the halogen that is group 17 elements. Now we will see the preparation of aryl halides. Aryl halides can be prepared by electrophilic aromatic substitution reaction, which is also known as direct halogenation. Why electrophilic substitution reaction in case of aryl halide is called direct halogenation? Because the electrophile is directly attached to the nucleus of aromatic ring, which give aryl halide as the product. For example, benzene react directly with chlorine or bromine in dark, at ordinary temperature, in between 310 to 320 Kelvin, in the presence of Lewis acid to form chloroprenes or bromoaryns respectively. Why Lewis acid is used in this reaction? This is due to two reasons. First one is, Lewis acid act as catalyst or halogen carrier, which carry the halogen to the aromatic hydrocarbon. And second reason is that it helps to generate electrophile, which attack the benzene ring, to form the product. Some example of Lewis acid are FeCl3, AlCl3, and FeBr3. In aromatic hydrocarbons, if one or more hydrogen atoms are replaced by halogen atom, then we get aryl halides. Halogens atom are belong to group 17 element. And these element are chlorine, fluorine, bromine, and iodine. By direct halogenation, we can prepare chlorobenzene and bromobenzene. But we cannot prepare aryl fluoride and iodoaryns. Aryl fluorides cannot be prepared by direct fluorination because F2 is very strong oxidant, which make the reaction violent. And iodoaryns cannot be prepared by direct iodination because the reaction is reversible. In order to avoid backward reaction, in case of iodoaryns, iodination is done in presence of oxidants, like iodic acid, nitric acid and mercuric acid. For example, if you are doing iodination as shown in the reaction by direct halogenation, though the reaction is reversible, equilibrium may shift in backward direction. That's why as soon as Hi will formed, it will react with oxidant, which oxidize high to I2 and equilibrium shift in forward direction. Reactivity towards nucleophilic substitution reaction. Here we will discuss the reactivity of aryl halide towards nucleophilic substitution and along with vinyl halide, allyl halide, and aryl halide. Aryl halide undergo electrophilic substitution reaction more easily, but nucleophilic substitution reaction are not shown by aryl halide. This is due to the inertness of halogen atom in aryl halide. This inertness of halogen atom is due to two reasons. Number 1, if you see the structure of aryl halide, the carbon atom is sp2 hybridized. The carbon-halogen bond is shorter, that is 1.68 angstrom. And this is due to the presence of double bond in aryl halide. So, the halogen atom in aryl halide is tightly held by carbon atom. Hence more energy is required to break this bond. Therefore halogen atom in aryl halide is difficult to be replaced by other nucleophile. Second reason is that if we will take an example of any aryl halide, like chlorobenzene, and draw the resonance hybrid structure, then we will find that, from structure 2 to 4, the chlorine atom is joined to carbon atom by a double bond. Due to this, chlorine atom come loser to carbon atom, and linked tightly to carbon. Therefore it is difficult to be replaced by other nucleophile. Now we'll discuss the reactivity of halogen in vinyl halide. Like aryl halide, nucleophilic substitution reaction are also not shown by vinyl halide. This is due to two reasons. Number 1, in vinyl halide, if you see the structure CH2 double bond CH single bond X, the carbon atom is sp2 hybridized, where P character is more, that is 66%. So the carbon atom, in vinyl chloride, is more electronegative. Due to this, electron pair between carbon and chloride atom is more attracted towards carbon atom. And CCl bond decrease to 169 picometer. So chlorine atom is tightly linked to carbon, and cannot be easily replaced by any other nucleophile. Second reason is that the electron pair on the halogen atom, in vinyl halide, is in conjugation with the pi electron pair of double bond in structure 1. We can draw the resonating structure of vinyl halide as shown in diagram. In structure 2, due to the presence of double bond between carbon and chlorine atom, the strength of its bond increases, and bond cleavage become difficult. Hence chlorine atom is not easily replaced by nucleophile. Next come to reactivity of halogen in allyl halide. Halogen atom in allyl halide is more reactive, and they are easily undergo nucleophilic substitution reaction. This is due to two reasons. Number 1, in allyl halide, the carbon atom directly linked to the halogen atom is sp3 hybridized. Due to this, see the diagram, the p orbital on second carbon cannot interact with p orbital of halogen atom. Therefore halogen atom in allyl halide is more reactive. The second reason is, when allyl halide ionizes, the allyl carbonium ion is formed, which is resonance stabilized. Therefore allyl halide undergo nucleophilic substitution reaction easily. For example, when allyl iodide ionize, it will give resonance stabilized allyl carbocation. Now we'll discuss the reactivity of halogen in aryl halide towards the nucleophilic substitution reaction. Aryl means it is a aromatic alkyl halide. Best example of aryl halide is benzyl chloride. The halogen atom in aryl halide is reactive like allyl halide. And during nucleophilic substitution reaction, the benzyl cation so formed in the first step is resonance stabilized. Therefore aryl halide undergo nucleophilic substitution reaction more easily. For example, when benzyl chloride ionizes, it gives benzyl carbocation and chloride ion. We can draw the resonating structure of aryl carbocation, which is resonance stabilized. Therefore it show nucleophilic substitution reaction. Last one is the reactivity of halogen in alkyl halide, towards nucleophilic substitution reaction. In alkyl halide, Rx, R is alkyl group and X is halogen. The halogen atom in alkyl halide is directly attached to carbon atom of alkyl group. Halogen being more electronegative than carbon, so the CX bond can be slightly polarized. Therefore the nucleophile, which are more basic than halogen atom, can attack the positively charged carbon with the removal of halide ion. In alkyl halide, the carbon atom is sp3 hybridized. And the carbon-halogen bond in alkyl halide is 1.80 angstrom. Therefore, the halogen atom in alkyl halide is reactive and halogen atom can be easily replaced by other nucleophile. Thank you.